As the title says, this video is going to guide you through the topic of short-run behavior of polynomial functions. To help with taking notes on this video, you should have the class notes and example sheet for section 11.3. Let's see, so back in chapter 3, you all had some experience with coming up with quadratic formulas or formulas for quadratic functions if you knew what the zeros were. And the way you did that was using factored form, right? That if you knew a zero was, say, at 1, then you knew one of the factors for that function was x minus 1. So use the same technique here. It's not a quadratic because, as you can see, we have 3 zeros. But see if you can come up with a formula for a polynomial that's got these 3 zeros using that same idea. Why don't you pause the video and give that a shot? Perhaps you came up with something like this. These 3 factors seem to work pretty well, right? We have our 0 at 4 with x minus 4, at 1 with x minus 1, and then, of course, this factor is x minus negative 2 to give you the 0 at negative 2. There is only one problem here, is in that we do have one more stipulation that we need to have a y-intercept at negative 16. So our graph should probably look something like this, although you'll have to ignore the waves, okay? Imagine this is a smooth curve. It's hard for me to draw something smooth with the pen on this iPad. Yeah, and of course we're going to have our y-intercept right here at negative 16, okay? Now, that's not exactly what we have right now. If you plug 0 into our formula up here, we're going to end up with, 0 plus 2. So 2 times negative 1 times negative 4. We're actually going to end up with y equal to 8, which looks more like the red graph here rather than the blue graph. So what can we do to our formula so that we'll end up with with the point 0, negative 16 on our graph without introducing any new factors here, right? We only want the 3 zeros that we already have. Well, hopefully you're remembering something about what we did back in chapter 3. There's one more component of this factored form here that we're missing, and that is the fact that there is always a possibility of some factor k being in the formula. This would be just some constant. So what could we let k be so that instead of having our y-intercept being at positive 8 up here, it's going to be down at negative 16. Well, certainly if you said that k should be negative 2, right, that should fix everything. So let's check this out. So we're saying our final answer here is negative 2 times x plus 2 times x minus 1 times x minus 4. And then when we check it out, I do believe we get negative 16 for our y-intercept. Okay, now there was another challenge to see if you could come up with a different formula that could still meet all 4 of these criteria. Okay, so this time we still need to have our zeros, our 3 zeros, so we still need to have a factor for each of those. But of course, if we just leave it like this, then we're going to end up having to have k be negative 2 and we have the same formula. So what is a way we could actually change one of these zeros without, we don't want to add any more zeros. I can't throw in somebody might think, well, let's just put an x in there. But if you put x in there, then you've got another 0 at x equal to 0. So we don't want to do that. But what could we do to change one of these zeros without affecting the fact that we actually have a 0 there? And I'm hoping that you're thinking, let's do something like this, where we just maybe, we could just add a square up here. Changing this to a square actually does not affect the fact that we have a 0 there, right? If we were to set y equal to 0 and solve, we'd still get x equal to 4 as one of our zeros. But we've definitely changed the formula and we'll end up with something different. Now, let's see. Are we still going to be having a y-intercept at negative 16? If we plug 0 in for x, we're going to have positive 2 times negative 1, which is negative 2. But this time it's not times negative 4, right? It's times negative 4 squared, or 16. So we're actually going to have negative 2 times 16, which gives us negative 32. So if you're thinking, yeah, let's just let k be 1/2 and that would solve our problem, then you are correct, because we can actually turn this into an algebra problem. We can put our k up here and then plug in our 0, and we will end up with negative 32 times k equals negative 16 when we plug 0 and negative 16 in. So k does need to be 1/2. All right, so what does that mean our graph is going to look like? So is our graph going to look the same as what we had before? Well, I think we can know it can't do that, because when we look at this formula now that we have and consider the long run behavior, it's not, this graph is behaving like a cubic or an odd degree, and we're not going to have that, right? We're going to have our leading terms can be 1/2 x times, in this case, x squared. And so our graph should actually be mimicking our long run behavior of 1/2 x to the 4th, right? And we know 1/2 x to the 4th should be going up at the end, right? So we are coming down, coming through, hitting negative 16, coming up to 1, but now something needs to change as we hit 4. So let's just check our positives and negatives as we're coming into 4. If we plug in something like 3, where our graph is saying we should get positive, so let's see, we'd have a positive factor here, a positive factor here, and then of course the square factor is always positive, so that's good. But now what about when we're leaving? If we plug in 5, we'll have positive, positive, and positive again, and of course 1/2 is positive. So that's the difference, right? Our graph should actually look like the following. And what we have here is called a double zero, where the graph just comes down and it kisses that x-axis and then goes right back up. And that's going to happen anytime you have, it's actually going to happen anytime you have an even exponent on one of your factors. All right, we'll look into that a little more later, but this is our graph here. I'll just mention at this point, there are a number of other ways we could have gone about approaching this problem. We could have actually had maybe a double zero at negative 2 and then come up and done something like that. Or we could have come down, negative 2, come here, had a double zero at 1, and then come up. So a lot of possibilities. Here are the graphs, these two graphs from the calculator. You can see both of them have the 3 zeros that we need, and then they both appear to be crossing the y-axis at negative 16. Okay, so let's organize some of our ideas here. I think most of this is found on page 452, that if we have a 0 at x equal to q, then x minus q is a factor, linear factor, and the converse is also true. All right, and of course this means that q0 is an x-intercept, and if you set the polynomial p of x equal to 0, you will get x equal to q as a solution. Extending what we did in chapter 3 with quadratics, we have now factored form for a polynomial, right, where z sub 1, z sub 2, and so on are the zeros. And of course, don't forget about that constant k that will be in front there. All right. Of course, this form is very useful when looking at what we call short-run behavior, which is talking about what's happening with like zeros and x-intercepts close to the origin. All right, so see what you can do with this one here. You have 3 zeros that you should be able to see. Each of these units on the x-axis is 1. And then you also want to make sure that your function does go through the point 1, 5. Pause the video and give this a try. All right, perhaps you got this far, but don't forget, we still need it to go through the point 1, 5, right? And I think if we plug 1 in for x here, we're going to end up with something a lot bigger than 5 out for y. So don't forget about this k number, right? We do need to have a constant in front of all those factors. So if you didn't figure out what k is, give that a shot now. Pause the video. All right, final answer looks like this. Perhaps the easiest way to solve for k is just to turn it into an algebra problem. You may not need this many steps, but get it down to the fact that k times some number, in this case it'll be 40, right? I forgot to mention, making sure you have the square on there, and that's going to cause this this factor to not be -2, but a 4, and you end up with k equal to 5/40, or 1/8. And then you have your final answer written down here. I want to just explore this concept of the repeated or multiple zero real quickly here. You can almost think of it as the result of two or more zeros merging. Like normally when we'd see like a quadratic or something with two zeros like here, they're separate. You can almost just think of them as coming together now, getting closer and closer to each other. And then at some point, they just merge and become 1, 0. And that's, of course, when the graph just comes down and touches the axis and goes back up. And, you can say the same thing over here about the cubic. This would be, of course, where you would have 3 different zeros, and, they come in closer to each other. P comes into here on the green graph, right? And then they just all 3 merge at the same time. And so you still have this concave down part of the graph, but then it changes to concave up right at the x-axis. And that's what happens when you have 3 zeros merging. So to summarize here, we have the double or even number 0, because this doesn't have to happen with a square. It can happen with 4th or 6th, but we have the graph just come down, kiss the x-axis, and then go back up. And of course, it could happen the other way. If your k value is negative, you might have something more like this, all right? And the graph touches the x-axis but does not cross, and the factor, of course, is going to be even. And just to kind of reiterate, the reason it doesn't cross, remember, as we were looking in the example before, is that by having an even exponent on it, it's going to keep whatever your difference is between x and c, it's going to keep it positive. So it's not going to change, the sign, the sign, as you go from the left of c to the right of c. Such is not the case, though, when it's a triple or an odd numbered 0, right? It will actually cross, because the sign's will change when you have an odd exponent. So the graph will cross. It'll look a lot like the cubic, whether it's going up or going down. It crosses the x-axis. N is odd on our exponent, on our factors. The last observation we'll make here is just in terms of what in general do these curves look like depending on what the degree is, right? So very quick observation we can make about some of these curves. Of course, first degree is going to look like that, right? Second degree look like that, and third degree could look like that. So the number of zeros we have on first degree is 1. No curves. It's linear, right? Number of zeros, second degree is 2. And of course, we need 1 curve to be able to have 2 zeros. And if we have 3 zeros, we need 2 curves, right, to be able to deal with that, right, to curve back and then curve back up. So what is the most number of curves or turning points that a 4th degree polynomial can have? Hopefully you said 3, right? Because if it can have 4 zeros, that means it can turn 3 times, once and twice and then 3 times. And of course, do we even need to draw the last one? The pattern is very clear, right? Every time you add a 0, you're going to have to have another curve. So there's always appears to be 1 fewer curve than the number of zeros that we can possibly have. So to sum up, right, if we have an nth degree polynomial, it's going to have n zeros, at most n zeros, and turn at most n minus 1 times. I want to focus real quickly on why we say at most in both of these cases. Just because we have a curve that looks parabolic, it does not mean it's a second degree polynomial, right? This could be x to the 4th, x to the 6th. So when we say at most, you have to keep in mind that a 4th degree can mimic a second degree, a 6th degree can mimic a second degree or a 4th degree, and so forth. And the same, of course, is true with the odd curves, right? If we see something like this, it looks it might look like it's cubic, but it could be 5th degree, it could be 7th degree. They do mimic ones that are a lower degree. All right, for the last example, we're going to turn things around and give you a formula and ask you to graph it. You can see it looks like it's in factored form, but we have that x squared minus 25. That looks a little different, right? That's not like x minus 25 is x squared. So think about what you can do with that. I'm giving you a hint that perhaps it still needs some more factoring here, right? You're done, to make sure you're done with your graph, make sure that all your x and y intercepts are labeled. All right, pause the video, give that a try, and then you can check it with what I've done. Thank you for doing that. Is this what you got? Okay, so let's take a look at this. This polynomial right here is not fully factored, right? We have a difference of squares binomial that we can split into x times x, and then we have -5 times +5, and of course the middle terms would cancel. So there we go. Now we have the full factors. So we have 3 zeros, one at -5, one at 4, and one at +5. And then before we sketch the curve, we should figure out the y-intercept. Now I didn't write that out, but it basically came down to 0 minus 4, so -4 times 0 minus 5, -5. Now that would be -4 times -5 is 20. And then times 5, which is 100. And then times another 5, which would be 500. So I just kind of did that in my head. I'm going to mark that. I'm not worried about the scale at all. My y scale can be completely different from my x scale. Okay, and then once we have that, we can actually sketch the curve and see that it's going to come up and hit that point and come back down and go through. We did not have any double zeros or double roots, so everything's going to cross the x-axis. Okay, one final check on our graph would be to look at the long run behavior. If we were to multiply all these terms out or all these terms out, our leading term would be 5 times x times x times x, or 5x cubed. That'd be the highest degree term we would have. And we just want to make sure that our graph basically behaves like 5x cubed would, and we know that 5x cubed would basically look like this, right? So I think we're good. It would be rising as x approaches infinity. We'd be going up, be rising up, and as x approaches -infinity, we would be going down. So I think our graph is well done. And here's the graph on our calculator. You can see we do have a y-intercept of 500 up there, right? And then our x-intercept at -5 and looks like 4 and 5. So I think that does it, and now you should have plenty of tools to work with both the long run behavior of polynomials and the short run behavior.